What if motion is not as simple as we believe? Do objects really follow single paths? Or is that just approximation? Why do we assume one trajectory? Because it matches daily experience. A ball goes from hand to ground, a planet orbits sun, a car drives on road. Single path seems obvious. But science often reveals deeper structure. Observation tells what happens. Theory explains how. Classical physics provided powerful rules. Newton described motion. For centuries, predictions worked. Technology advanced. Engineering flourished. Yet experiments at microscopic scale revealed anomalies. Light behaved strangely, sometimes like particle, sometimes like wave. Double-slit experiment demonstrated this. Light passing through two openings created interference. Bright and dark patterns. If light were tiny balls, pattern would differ. Two simple bands expected, one for each slit. Instead we observe fringes. Evidence of wave behavior. Waves interfere. They add. They cancel. This phenomenon challenged intuition. Because particles and waves seem distinct, classical categories failed. New framework required. Quantum mechanics emerged. It did not discard classical physics, it extended understanding. At small scales, rules differ. Probabilities replace certainties. Superposition replaces single state. Objects exist in combinations of possibilities. Measurement selects outcome. But before measurement, multiple possibilities coexist. This is difficult to visualize. Human intuition prefers concrete images. A thing here? Not both here and there. Yet experiments confirm quantum predictions. Electrons produce interference patterns. Photons exhibit wave behavior. Atomic energy levels are discrete. Quantization appears. Nature seems to use mathematics beyond simple geometry. Here deeper question arises. What causes interference? Why do probabilities combine strangely? To answer, physicists reconsidered fundamentals. Instead of single trajectory, consider all possible trajectories. Every path contributes amplitude. Not metaphor. Mathematical summation. Each path assigned phase. Phase derived from action. Action is integral of kinetic minus potential energy. Divide by Planck's constant. Inserting complex exponential. Result is amplitude. Summation of amplitudes yields probability. This is path integral formulation. It reframes motion. Particles do not choose one route. They explore all routes. But contributions interfere. Most cancel. Only near stationary actions survive. Stationary means small variations change nothing. This connects to principle of least action. Classical mechanics emerges as limit. When action is large relative to quantum scale, phase oscillates rapidly. Cancellation dominates. Single trajectory appears. Deterministic laws hold approximately. Thus classical world is emergent. Quantum world is fundamental. Both consistent. Different regimes understanding this resolves paradox. Why large objects behave predictably? Because countless quantum contributions cancel. Why small objects show uncertainty? Because cancellation incomplete. Interference visible. Science progresses by recognizing limits. Old theories remain useful approximations. New theories expand scope. Knowledge grows. Human understanding deepens. This journey continues. Questions remain. Research ongoing. Physics seeks unification. Deeper principles. Nature's ultimate laws. One influential idea in this journey came from modern physics. A scientist who reformulated quantum mechanics. He emphasized summation of histories. Paths rather than single trajectories. His insight changed methodology. It simplified complex calculations. It provided conceptual clarity. This physicist is Richard Feynman. His contribution remains central. Path integrals underpin quantum field theory. Particle interactions, statistical mechanics, many domains. They illustrate power of perspective. Sometimes reframing question unlocks solution. Instead of asking which path, ask how all paths contribute. Instead of single answer, consider ensemble. This is scientific creativity. Evidence still rules. Mathematics still guides, but ideas evolve. Understanding expands. Classical intuition suggests single paths. Objects move from start to finish. Deterministic trajectories. Predictable outcomes. This works at human scale. Engineering relies on it. Bridges stand. Planes fly. Buildings remain stable. Classical physics approximates reality here. But at microscopic scale, behavior differs. Experiments reveal quantum effects, interference patterns, superposition, probability distributions. These results cannot be explained by single trajectories. Instead, quantum mechanics describes possibilities, not certainties. Particles exist in combinations of states. Wave functions represent amplitudes. Mathematical objects encoding probability information. Measurement extracts outcome. Before measurement, multiple possibilities coexist. This is not contradiction. It reflects nature structure. Double-slit experiment illustrates idea. Light through two openings produces fringes. Bright regions where amplitudes reinforce. Dark regions where they cancel. If light were tiny balls, two bands expected, one for each slit. Experiment shows more complex pattern. Evidence of wave-like behavior. Waves interfere. They combine, they subtract. Resulting pattern encodes probability. This demonstrates superposition. Particles behave like waves of possibility, not classical objects. Quantum mechanics formalizes this. Wave functions evolve according to Schrödinger equation. Deterministic evolution of probabilities, not deterministic evolution of positions. This distinction matters. Classical determinism describes outcomes. Quantum determinism describes amplitudes. Outcomes remain probabilistic, but probabilities evolve predictably. Science uses mathematics to compute them. Predictions match experiments. Technology validates theory. Semiconductors rely on electron behavior. Energy bands arise from quantum rules. Transistors control current. Computers process information. All built on quantum principles. This connection demonstrates practical value. Abstract ideas enable innovation. Knowledge transforms society. Now deeper conceptual layer. Summation of histories approach. Reformulates quantum mechanics. Instead of single path, consider all paths. Each path contributes amplitude. Phase determined by action. Action is integral of Lagrangian. Kinetic minus potential energy over time. Divide by Planck's constant. Insert into exponential. Summation yields probability. Interference naturally arises. Paths with rapidly varying phase cancel. Stationary paths dominate. This connects to classical principle. Least action. Classical mechanics states nature follows path minimizing action. Quantum mechanics explains why approximation works. Because non-stationary paths interfere destructively. Only near stationary action contributions survive. Thus classical trajectory emerges. Determinism appears. But underlying structure remains quantum. This insight unifies perspectives. Classical and quantum not enemies. They describe different limits. Large-scaled classical. Small-scaled quantum. Understanding limits prevents confusion. Science progresses by recognizing scope. Old theories remain valid within domain. New theories extend domain. Knowledge cumulative. Human understanding evolves. Historically, physics transformed repeatedly. Newtonian mechanics revolutionized motion. Maxwell described electromagnetism. Relativity redefined space and time. Quantum mechanics revealed microscopic structure. Each advancement expanded comprehension. Not replacement of all previous ideas. Refinement, extension, integration. Modern physics builds on foundations. Researchers continue exploration. Unanswered questions persist. Quantum gravity seeks unification. General relativity describes space-time curvature. Quantum mechanics describes microscopic behavior. Combining them remains challenge. Theoretical proposals exist. String theory. Loop quantum gravity. Other approaches. Evidence still developing. Science remains open. This openness is strength. Ideas tested against observation. Successful theories retained. Failed ideas discarded. Understanding improves. Now recognize individual contributions. Scientists shape progress. Among them stands influential thinker. Known for creativity and clarity, he simplified complex problems, introduced diagrams for interactions, reformulated quantum mechanics. Summation of histories became tool. His pedagogy inspired generations. He emphasized reasoning, not memorization. He valued curiosity, questioning assumptions. This physicist is Richard Feynman. His legacy endures. Physics education incorporates his methods. Diagrams remain standard. Path integrals advances because of such insight. Understanding deepens. Technology benefits. Human knowledge grows. Quantum mechanics initially appeared strange. probabilities instead of certainties, superposition instead of single states, interference instead of simple addition. But mathematics revealed consistency. Predictions matched experiments. Technology validated theory. Understanding improved. One powerful formulation is summation of histories, also known as path integral approach. Instead of single trajectory, consider all possible trajectories. Every path contributes amplitude. Amplitude is complex quantity. It carries magnitude and phase determined by action. Action is integral of Lagrangian. Kinetic minus potential energy over time. Divide by Planck's constant. Insert into exponential function. Result, amplitude t. This expression encodes contribution. Different paths yield different phases. When summing amplitudes, interference occurs. Some paths reinforce, others cancel. Total probability emerges after summation. Square magnitude gives likelihood. This procedure explains double-slit results. Also explains classical limit. When action is large relative to quantum scale, phase oscillates rapidly. Neighboring paths cancel. Only stationary contributions remain. Stationary means small variations change nothing. This is principle of least action. Classical mechanics states nature follows such paths. Quantum formulation explains why approximation works. Because destructive interference removes alternatives, single trajectory dominates. Thus classical world appears deterministic. But underlying process remains probabilistic. This duality resolves conceptual tension. Determinism at macro scale, probability at micro scale, both consistent within limits. Science often encounters such layered structure. Thermodynamics emerges from statistical mechanics. Gas laws describe average behavior. Molecules obey microscopic rules. Averaging produces macroscopic laws. Similarly, classical physics emerges from quantum rules. Different levels of description. Hierarchy of models. Each valid in domain. Summation of histories provides insight. Particles do not choose one path. They explore possibilities. Interference selects outcomes. Observation reveals result. Before observation, superposition existed. After observation, recorded event. This does not imply multiple realities in everyday sense. It implies richer mathematical structure. Wave function encodes possibilities. Measurement extracts information. Decoherence explains emergence of classicality. Environmental interactions entangle states. Information disperses. Coherent superposition becomes effectively inaccessible. Classical record forms. This modern understanding avoids mystical collapse. Quantum mechanics remains consistent. Predictions match experiment. Philosophical interpretation varies. Science focuses on results. Models that work are retained. Those that fail are revised. Path integral formulation contributed significantly. It simplified calculations, provided conceptual framework, connected quantum and classical ideas, enabled progress in particle physics. Quantum field theory uses similar methods. Interactions described by diagrams. Each diagram represents history. Contribution computed mathematically. Summation yields amplitude. Predictions tested experimentally. Colliders like Large Hadron Collider study particles. Data compared with theory. Agreement validates framework. Discrepancies inspire new research. Knowledge advances. Now appreciate historical context. Earlier physicists confronted anomalies. Blackbody radiation. Atomic spectra. Classical theories failed. Quantization introduced solution. Energy discrete. Photons carry packets. Electrons occupy orbitals. Quantum rules emerged. Initially counterintuitive, later acceptive evidence compelling. Science adapts. This adaptability is strength. Understanding evolves. No idea is sacred, only evidence matters. Among contributors to quantum understanding, one figure stands prominent. He reframed problems creatively, emphasized summation of paths, introduced diagrams simplifying interactions. His teaching style inspired generations. He communicated complex ideas clearly. He valued curiosity, questioning assumptions. This physicist is Richard Feynman. His legacy influences modern science. Path integrals remain fundamental. Diagrams standard in research. Educational methods reflect his clarity. Physics continues to build on ideas, not because they are perfect, because they work. Science progresses by refinement. New data guides theory. Theory guides prediction. Prediction guides experiment. Cycle continues, human knowledge expands. Technological applications follow. Quantum mechanics enables innovation. Semiconductors, lasers, medical imaging, computing. Advancements improve life. Understanding nature yields benefit. Curiosity drives discovery. Discovery drives progress. This narrative illustrates science's power. Ideas transform society, evidence shapes belief. Mathematics describes reality. Physics advances when ideas change perspective. Old models describe observations. New models explain deeper structure. This process repeats historically. Newton described motion with remarkable accuracy. Planets, projectiles, forces. Deterministic equations, predictable results. For centuries this framework worked, but anomalies appeared at microscopic scale. Light behaved unexpectedly. Electrons showed wave properties. Energy quantization emerged. Classical ideas required extension. Quantum mechanics provided framework. It did not destroy classical physics. It generalized understanding. Classical laws remain valid limits. When quantum numbers large, behavior approximates determinism. When small, probabilistic effects dominate. This duality illustrates hierarchy of theories. Different levels describe different phenomena. No single description covers everything. Science accommodates complexity. Mathematics expresses relationships precisely. Experiments verify predictions. Knowledge accumulates. Path integral formulation contributed significantly. It reframed quantum mechanics. Instead of differential equations alone, consider summation of histories. Every possible path contributes amplitude. Phase determined by action. Interference shapes outcomes. Most paths cancel. Stationary contributions remain. This explains classical emergence. Large systems average out quantum effects. Small systems reveal them. Understanding this removes confusion. Quantum mechanics is not mystical. It is mathematical description. Probability replaces certainty. Superposition replaces state. Observation selects outcome. Before observation, possibilities coexist. After observation, recorded result. Decoherence explains classical appearance. Environmental interactions entangle states. Information disperses. Coherent superposition becomes inaccessible. Classical record forms. No paradox required. Modern research continues exploring foundations. Quantum computing exploits superposition. Information encoded in quantum states. Operations performed simultaneously on possibilities. Potential computational advantages. Engineering challenges remain. Decoherence and error correction. Progress ongoing. Scientific innovation thrives on such challenges. Historically, ideas once controversial become standard. Earth orbit around Sun. Atomic structure. Quantum behavior. Each accepted after evidence. Understanding evolves. Perspective shifts. Now recognize individual contributions. Scientists shape progress. Among them stands influential thinker. He simplified complex problems. Introduced diagrams representing interactions. Emphasized intuitive understanding. Reformulated quantum mechanics. Summation of histories became tool. His teaching inspired generations. He communicated with clarity. He valued reasoning. He discouraged rote memorization. This approach remains valuable. Education should foster understanding, not mere formula application. Physics becomes accessible when ideas clear. Mathematics supports reasoning. Concepts guide intuition. This balance essential. The physicist in question is Richard Feynman. His legacy endures. Research builds on insights. Diagrams standard in calculations. Path integrals fundamental. Pedagogy reflects his style. Curiosity encouraged. Questions valued. Science thrives on inquiry. Now broader reflection. Nature is intricate, sometimes counterintuitive, but comprehensible. Mathematics provides language. Experiments provide evidence. Theory provides explanation. Together they form knowledge. Human understanding progresses. Challenges remain. Unanswered questions drive research. Quantum gravity seeks unification. General relativity describes space-time curvature. Quantum mechanics describes microscopic behavior. Combining them remains difficulty. Various approaches explored. String theory, loop quantum gravity, others. Evidence still developing. Science remains open. This openness is strength. Ideas tested. Successful theories retained. Failed ideas revised. Knowledge improves, technology benefits, society advances. Consider practical impact. Quantum principles enable devices. Semiconductors revolutionized electronics. Computers process information. Communication networks connect world. Medical imaging saves lives. Laser technology diverse applications. Fundamental research yields practical outcomes. Investment in knowledge important. Curiosity leads to discovery. Discovery leads to innovation. Innovation improves human condition. This narrative illustrates science's value. Understanding nature enriches life. Not only materially, also intellectually. Perspective expands. Wonder persists. The universe remains fascinating. Exploration continues. Physics is a journey of ideas. Human beings observe nature. We detect patterns. We build explanations. These explanations become theories. Theories predict outcomes. Experiments test predictions. When results match, knowledge strengthens. When results differ, theory evolves. This cycle defines scientific progress. Classical physics once described motion with precision. Objects followed single trajectories. Forces produced acceleration. Equations predicted positions. This framework enabled engineering, bridges, machines, planetary calculations. Human technology advanced, but as observation reached microscopic scale, classical ideas encountered limits. Light behaved unexpectedly, sometimes like particle, sometimes like wave. Double-slit experiments revealed interference. Patterns incompatible with single-path thinking. Electrons also displayed wave properties, not only photons. Matter itself exhibited superposition. Probability patterns replaced deterministic expectation. This was revolutionary. Scientists needed new mathematics. Quantum mechanics emerged. It did not discard classical knowledge. Instead, it extended understanding. Classical laws remain valid limits. When systems are large, quantum effects average out. Deterministic behavior appears. When systems are small, quantum effects dominate. Probabilities govern outcomes. This duality is essential. It resolves apparent contradictions. Science accommodates different scales. No single description suffices for all regimes. Quantum mechanics introduced wave functions, mathematical objects encoding probability amplitudes. They evolve according to precise rules. Schrödinger's equation governs dynamics. Deterministic evolution of amplitudes, not deterministic evolution of positions. This distinction matters. Outcomes remain probabilistic, but probabilities evolve predictably. Experiments confirm predictions. Technology exploits principles. Semiconductors rely on electron behavior. Energy bands arise from quantum rules. Transistors control information. Computers process data. Modern society depends on these inventions. Fundamental research produces practical benefit. Knowledge and application interact. Path integral formulation further advanced understanding. Instead of focusing solely on differential equations, it considered summation of histories. Particles do not traverse single path. They explore all possible paths. Each path contributes amplitude. Phase determined by action. Action is integral of Lagrangian. Kinetic minus potential energy over time. Divide by Planck's constant. Insert into complex exponential. Result is contribution. Summation of contributions yields probability. Interference occurs naturally. Some paths reinforce, others cancel. Total outcome reflects combined effect. This explains double-slit results. Bright and dark fringes. Not mysterious behavior. Mathematical consequence. Superposition and interference. Path integrals explain classical emergence. When action is large relative to quantum scale, phase oscillates rapidly. Neighboring paths cancel. Only stationary contributions remain. Stationary means small variations do not change result. This is principle of least action. Classical mechanics expresses same idea. Nature appears to follow path extremizing action. Quantum formulation clarifies why approximation works. Because destructive interference removes alternatives. Single trajectory dominates. Thus classical world emerges. Deterministic behavior appears. But underlying process remains quantum. This hierarchical understanding is powerful. Different descriptions for different scales. No contradiction. Physics accommodates complexity. Models remain valid within domains. Science advances by recognizing limits. Old theories provide approximations. New theories extend scope. knowledge evolves. Historically, ideas transformed understanding. Newton described motion. Maxwell unified electricity and magnetism. Einstein redefined space and time. Quantum mechanics revealed microscopic structure. Each advancement expanded perspective. Not replacement of all prior knowledge. Refinement and extension. Human comprehension deepened. Technology benefited. Society progressed. Among contributors to quantum understanding, one physicist stands out for clarity and creativity. He simplified complex problems, introduced diagrams representing interactions, emphasized intuitive reasoning, reformulated quantum mechanics. Summation of histories became practical tool. His teaching inspired generations. He communicated ideas with precision. He valued questioning. He discouraged rote memorization. Understanding mattered. This approach remains valuable. Education should foster insight, not mere formula application. Concepts should be grasped. Mathematics supports reasoning. Ideas guide interpretation. This balance is essential. The physicist responsible for significant contributions is Richard Feynman. His legacy persists. Path integrals remain fundamental. Diagram standard in research. Pedagogical methods influence teaching. Science continues building on insights. Ideas evolve. Understanding deepens. Unanswered questions remain. Quantum gravity seeks unification. General relativity describes spacetime curvature. Quantum mechanics describes microscopic behavior. Combining frameworks remains challenge. Theoretical proposals exist. String theory. Loop quantum gravity. Other approaches. Evidence continues accumulating. Science remains open. This openness is strength. Hypotheses tested, successful ideas retained, failed ideas revised. Knowledge improves. Human understanding expands. Practical applications arise. Quantum principles enable innovation. Semiconductors transform technology. Communication networks connect world. Medical imaging improves diagnostics. Lasers enable precision tools. Computing processes information. Fundamental research yields societal benefit. Investment in knowledge important. Curiosity drives discovery. Discovery drives progress. Progress enhances human capability. Yet science also enriches perspective. Understanding nature inspires wonder. The universe is intricate. Patterns emerge. Mathematics describes relationships. Experiments validate theories. Knowledge reveals structure. Humanity participates in exploration. Questions guide inquiry. Answers generate further questions. This cycle continues. Future discoveries await. Quantum computing may transform computation. New materials could revolutionize engineering. Energy solutions may address challenges. Science offers possibilities. Responsible application matters. Knowledge requires wisdom. Technology should serve humanity. Ethics and understanding coexist. In conclusion, physics illustrates power of ideas. Observation leads to questions. Questions lead to theories. Theories lead to predictions. Predictions tested by experiment. Knowledge refined. Understanding deepened. The journey continues. Nature remains fascinating. Exploration persists. Human curiosity endures.